This is lecture 5F on integration failures. The purpose of this lecture is to show you, well, let you know that you don't know everything. Maybe you didn't need a lecture on that. But once you learn to integrate, you might come upon situations where you can't find a solution, and that is perfectly normal. Integration is not guaranteed. Just because you write the problem doesn't mean you can solve it. But there are several levels of failure. The first level is that there is no closed form solution. What is a closed form? That is some algebraic combination of these algebraic or transcendental functions like logarithms, exponents, polynomials, trig functions, and hyperbolic functions. If you can take those elementary transcendental functions and the algebraic functions and make some arbitrary combination of those, then you call it a closed form solution. That combination would include addition, subtraction, multiplication, division, roots, and powers. Right. So if you've constructed that, well, and composition too. So if you've constructed that, you call that a closed form solution. That might be almost impossible to find, but the idea is that sometimes you cannot find something like that. If you can find it, you say the integral has a closed form solution, and you print that up and put it in a handbook or tables or the back of the textbook. So one level of failure is that there is no closed form solution. In this class, the integrals have closed form solutions. They were specially engineered to have those. Of course, some are obvious and some you had to use substitution to find. In Calculus 2, you'll be introduced to more techniques for finding closed form solutions. But actually, many, if not most, integrals do not have closed form solutions. They still may be integrated, but you have to use a different method. One method that has been developed is to just construct special functions that are considered to be the primitive of certain very important integrals. Just like the log functions are constructed to be the inverse of exponentials. Even though there's no way to compute them, you can draw them and you store their values. Similarly, there are other functions such as the error function, gamma function, there's Bessel functions. All these functions are just names for the values of these integrals. And their values are stored in tables, or now they're stored in calculators. They do that, it's as though they're creating a new transcendental function, but they do it because that integral appears so often. The error function is like the most common example. The error function, which has a long name again, it's a function, is defined as the integral from 0 to x of 2 over the square root of x times e to the minus t squared dt. You would think that would have a nice solution, but it doesn't. Okay, and its solution is called the error function. You don't have to know this for the class. I just want you to know that such things exist. What is that e to the minus t squared? That is your normal or Gaussian distribution. So if you are in, well, statistical mechanics, economics, psychology, whatever field you're in, you might have that normal Gaussian distribution, that normal Gaussian curve. What if you wanted to integrate? You wanted to find the area underneath that curve? If this were test scores and you wanted to go from here to here, you wanted to know the number of test scores, the number of people who would have a test score in this range, you would want to integrate that. Okay, and the answer to that integration would be the error function, which you would have to look up, or it's probably stored already in your calculator. Here is a plot of the error function. All right, it's the integral of the Gaussian distribution. The reason it's called the error function, you might wonder about that. If you have a measurement, if you take a lot of measurements of the same thing and you have some error bars, if you have a Gaussian distribution of error bars about, of the inaccuracies in your measurement, and say they would fall into a Gaussian distribution, that's why it's called the error function, because those error bars, on a measurement are the inaccuracies or the potential inaccuracies of the measurement. It doesn't have anything to do with the Gaussian distribution in psychology. It has to do with actual measurements in a lab and the distribution of errors, potential errors in that measurement. Now, if you can't find a closed form solution and no one else has come up with a function and stored its value somewhere for you, you can integrate the function just by using Remont Integration. This is especially true if you have a limited number of jumps or discontinuities in the function. It helps that the function's bounded. And then you can compute the area as the limit of the area of triangles as a number, or rectangles as the number of rectangles approaches infinity. So this is something you could do on a computer as you keep getting smaller and smaller in those, in that number in the size of the rectangles. You should, if this is going to converge, you should see the answers converging onto a number. At some point you can say that's good enough and I'll take that as my answer. So that's a numerical way to evaluate an indefinite integral, a definite integral. So of course it doesn't work for an indefinite integral, because in an indefinite integral you're looking for a functional form. Remont integration is for definite integrals where you want a number. Now some functions fail to be Remont integrable, but there's another numerical technique called LeBlanc integration. It's similar to Remont integration, except you set the mesh over the y-axis. So this would be Remont integration. You see, you've divided the x-axis up and created the rectangles. Their long axis is vertical. Now here's LeBlanc integration. You see, you've divided up the y, you've divided up the range of the function, and then the long axis of the rectangles is more horizontal. So many functions are LeBlanc integrable that were not Remont integrable. So in other words, you have another way to evaluate the integral numerically. We worked on Taylor series approximations. In a Taylor series, you've approximated the function by a polynomial. You know how to integrate polynomials, so if you use the Taylor series approximation, you can just integrate the Taylor series term by term. And then there's some functions that can't be integrated at all. For example, 1 over x. All right, if you're integrating from 0 to some value a, cannot be integrated. Why? Because there's a vertical asymptote at x equals 0. So remember, when we were working with limits, we accepted infinity. Once we get to the derivative, continuity, or integrals, we don't accept infinite. And the problem here is that we would have the area under the curve would be infinite. We don't accept that as an answer in integration. So you say that function cannot be integrated. We reject the answer of infinity. And there's others that can't be integrated at all because they have an oscillatory discontinuity. A classic example is with function that's 1 when x is rational, 0 when x is irrational. It's not Remont integrable because you can never find any little areas to start putting your rectangles to even approximate this. Any approximation is so far wrong it doesn't make any sense. Some people, though, think they can finesse an answer for such cases because there are more irrational numbers than there are rational ones. So, and perhaps they're right on that. Also, there's no Taylor series approximation here since this function is not differentiable. Remember, Taylor series is based on taking the derivatives of the function. So those are just little bits of information about situations in which the integration does not proceed as planned. Just wanted to let you know about them when you go to other classes, so you can study them more as you go further in science and in mathematics.